On the night of October 22nd, 2025, the night over Earth was ordinary. Cities slept, telescopes silently watched the stars, and it seemed that space was just continuing its eternal, unhurried motion. But at a distance of 150 million kilometers from us, on the surface of our sun, something completely different was happening. The magnetic fields of the corona suddenly compressed, twisted into an invisible spiral, and then exploded outward. 1 billion tons of superheated plasma, magnetized to the limit, tore away from the solar corona and rushed into the depths of space at a speed of nearly 1,000 kilometers per second. This was a coronal mass ejection, a CME, as scientists call it, one of the most powerful phenomena in our star system. And this time, the trajectory of the cloud wasn't pointing toward Earth, not toward Mars or Venus, but toward something far more mysterious, toward interstellar comet 3I Atlas, a visitor from beyond our cosmic home, which came to us from the void between the stars. Write in the comments where you're watching this video from and what time it is for you. Because today, we'll be spending several hours together, diving into one of the rarest cosmic events in human history. To understand the full significance of what happened, we need to go back a few months. On July 1st, 2025, in Chile, at one of the Atlas telescope system stations, automatic sensors detected a new object in the sky. At first, it was just a glowing point, barely distinguishable against the background of stars. Astronomers checked the data, compared the trajectory, calculated the orbit, and realized that this wasn't an ordinary asteroid or a comet from the Oort cloud. The orbital eccentricity exceeded 1, which meant only one thing. This object came from outside, from interstellar space. The third confirmed interstellar visitor after Oumuamua and Comet Borisov. It was named 3I Atlas, the third interstellar object discovered by the Automated Asteroid Detection System. And within just a few weeks of observations, it became clear that this comet was special. Its coma, the gaseous envelope around the nucleus, glowed with a strange, almost emerald green color. This was the glow of dicarbon molecules, the very substance that gives many comets their characteristic shade. But in the case of 3I Atlas, the green was especially bright, especially saturated, as if the comet carried within itself a chemical composition unfamiliar to our system. The shape of the nucleus also turned out to be unusual. Preliminary calculations showed that Comet 3I Atlas has an elongated, stretched structure, possibly the result of millions of years of drifting in the interstellar void, where gravity and collisions with cosmic dust slowly shaped its appearance. Imagine a cosmic iceberg several kilometers long, composed of frozen gases, water ice, carbon dioxide, methane, and organic compounds that had never known the warmth of our sun. This object was born somewhere out there, in the depths of another star system, perhaps millions or even billions of years ago. Some catastrophe, possibly a gravitational disturbance from a passing star or a supernova explosion, ejected it into interstellar space. And now, having traveled unimaginable distances in absolute darkness and cold, the comet was approaching a star for the first time in its entire history. Our sun. In the summer of 2025, 3I Atlas entered the inner part of the solar system. Its icy surface began to warm up, evaporate, ejecting jets of gas and dust into space. The comet's tail, directed away from the sun by the solar wind, stretched for millions of kilometers. By mid-October 2025, Comet 3I Atlas found itself in solar conjunction. It was on the same side of the sun as Earth, but behind our star from our point of view. This meant that most ground-based telescopes couldn't observe it directly. The sun, with its bright light, eclipsed everything near it in the sky. The only way to see the comet during this period was through spacecraft, particularly the GOES-19 satellite, an American geostationary weather satellite that was in the perfect position to observe the region of space near the Sun. Its instruments, designed to monitor solar activity and weather, accidentally became humanity's only eyes directed at the interstellar comet. And it was GOES-19 that first recorded what happened on the night of October 22nd. In one of its images of the solar corona, a giant structure suddenly appeared, a bright, expanding cloud of plasma bursting from the Sun's surface, a coronal mass ejection. And its trajectory was directed exactly where Comet 3I Atlas was located. When the data from GOES-19 arrived at processing centers, astronomers and solar plasma physicists around the world froze. This had never happened in the history of observations. Yes, coronal mass ejections occur regularly. The Sun ejects 1 to 3 CMEs per day during periods of high activity. Yes, comets regularly pass near the Sun, sometimes even crashing into it or being destroyed by proximity. But for a powerful coronal mass ejection to head directly toward an interstellar comet, and at a moment when humanity has the tools to observe it, this was unprecedented. Russian astronomers from the Space Research Institute of the Russian Academy of Sciences promptly confirmed the data. International observatories, the Solar and Heliospheric Observatory SOHO, the LASCO coronagraphs, began tracking the movement of the plasma cloud. Calculations showed that the CME was moving at a speed of about 900 kilometers per second. With these parameters, it would reach the comet's orbit in approximately 48 hours. That is, on October 24th, 2025, humanity would witness a direct collision of a solar storm with an object from another star system. What is a coronal mass ejection from a physics standpoint? Imagine a giant bubble of magnetic field filled with charged particles, protons, electrons, ions of various elements. This bubble is born in the solar corona, the outermost part of the Sun's atmosphere, where the temperature reaches 1,000,000 degrees Celsius. When the magnetic fields on the Sun become too stressed, due to the star's rotation, due to the movement of plasma within it, they intertwine, twist, like a rubber band that's been wound to its limit, and at some point, that rubber band snaps. The energy accumulated in the magnetic field is released instantly, ejecting an enormous amount of matter into space. The mass of one ejection can reach 1 billion tons. That's more than the mass of all the icebergs in Antarctica. And all this matter moves through space, carrying with it magnetic fields that can interact with any object in their path. When a CME reaches Earth, and this happens regularly, it causes geomagnetic storms, auroras, and can disrupt satellite operations and communication systems. But our planet is protected by the magnetosphere, a powerful magnetic shield that deflects most of the charged particles. Comet 3I Atlas has no such protection. A comet is a fragile object. Its nucleus consists of ice and rock wrapped in a coma, a cloud of evaporating gas that extends for hundreds of thousands of kilometers. It has a tail, or rather 2 tails. One is dust, consisting of tiny particles that reflect sunlight and create a bright, curved plume following the comet's orbit. The second is ionic, consisting of ionized gas molecules that glow under the influence of the Sun's ultraviolet radiation. The ion tail always points strictly away from the Sun because the solar wind, a constant stream of charged particles from the star, blows it away. This tail can reach tens of millions of kilometers in length, but it's so rarefied that its density is comparable to the best vacuum we can create in a laboratory. And it's this tail that will first encounter the coronal mass ejection, when a dense cloud of magnetized plasma moving hundreds of times faster than the normal solar wind, slams into the rarefied structure of the comet's ion tail, something impressive will happen. The magnetic fields of the CME will begin to interact with the ionized particles in the tail, restructuring them, twisting them, possibly even completely tearing the tail apart. This phenomenon is called a disconnect event. Astronomers have observed it in comets before, when boundaries of interplanetary magnetic field sectors or particularly strong solar wind streams passed through them. The comet's tail suddenly detaches from the nucleus, drifts into space like a ghostly plume, and the comet begins to form a new one. It's a stunning sight, and can even be seen with amateur telescopes if the comet is bright enough. But with 3-eye atlas, everything will be much more intense. The coronal mass ejection carries energy equivalent to the explosion of billions of nuclear bombs. When this energy is transferred to the comet's gases, they'll begin to glow brighter. Fluorescence, the glow of molecules under the influence of high-energy particles, will intensify many times over. Perhaps the comet will become visible even from Earth, despite its proximity to the Sun, if its brightness increases sufficiently. Additionally, the extra energy transferred to the nucleus through interaction with plasma may enhance the sublimation of ice, the process where ice transitions directly to gas, bypassing the liquid phase. The comet will begin to evaporate faster, ejecting more gas and dust, increasing its activity. And here it's important to emphasize one detail that will reassure those worried about Earth's safety. This coronal mass ejection is directed at the comet, not at our planet. The geometry of the solar system at this moment is such that the CME's trajectory leads away from Earth. We won't be in the path of this plasma cloud. There will be no geomagnetic storms, no threats to satellites or power grids from this particular ejection. It's simply a cosmic coincidence, a rare opportunity to observe how solar activity affects an interstellar object. For scientists, this is a gift, a chance to study how solar storms influence comets that were born in other star systems, that have perhaps a different chemical composition, different physical properties. The data obtained during this event will help us better understand the nature of interstellar objects, the mechanisms of their interaction with stars, and the evolution of matter in the galaxy. To understand what exactly happened on the night of October 22nd, we need to look into the very nature of our sun. This star, which appears to us as a calm yellow disk in the sky, is actually a raging ocean of plasma, where processes of unimaginable power occur every second. At the sun's center, 700,000 kilometers below the visible surface, the temperature reaches 15 million degrees Celsius. There, in this thermonuclear hell, hydrogen atoms fuse into helium, releasing energy that then slowly, over thousands of years, works its way to the surface. But when this energy finally reaches the sun's outer layers, something strange begins. The temperature doesn't drop as you might expect, but instead, sharply increases. The sun's visible surface, the photosphere, has a temperature of about 6,000 degrees, but the outer atmosphere, the solar corona, is heated to 1,000,000 degrees and higher. This is one of the greatest unsolved mysteries of solar physics, which scientists have been struggling with for decades. In this superheated corona, magnetic fields of colossal strength are born. They penetrate the sun through and through, creating loops, arches, and the most complex structures that govern the movement of plasma. Plasma isn't just hot gas. It's a state of matter where electrons are torn from atoms, creating a sea of charged particles that react to magnetic fields. And these fields are constantly changing, because the sun rotates, and unevenly at that. The equator spins faster than the poles, This differential rotation twists the magnetic lines like ropes that are twisted again and again. After some time, the tension becomes unbearable. Magnetic fields rise to the surface, creating dark spots, regions where magnetic pressure suppresses convection and makes the surface cooler and darker. Energy accumulates around these spots, like a spring compressed to its limit. And when this spring releases, a coronal mass ejection occurs. 1 billion tons of plasma at a speed of 1,000 kilometers per second rushes into space, carrying with it twisted magnetic fields. The first observations of coronal mass ejections were made only in the 1970s, when spacecraft first got the ability to look at the sun without being blinded by its brightness. Before that, scientists knew about solar flares, sudden bursts of electromagnetic radiation, visible as bright flashes of light on the sun's surface. But CMEs turned out to be a completely different phenomenon. A flare is an explosion of energy in the form of light, X-rays, and gamma rays that lasts minutes or hours. A coronal mass ejection is a physical ejection of matter that can continue for hours and spread across millions of kilometers. Sometimes a flare and CME happen simultaneously, sometimes separately. The coronagraph aboard the Skylab space station, launched in 1973, first captured these giant clouds of plasma leaving the sun. Since then, every solar observatory, from SOHO, launched in 1995, to the Solar Dynamics Observatory in 2010, has been observing and cataloging these events. Over the past 50 years, scientists have accumulated a huge database on coronal mass ejections. It's known that their frequency depends on the 11-year solar cycle, the period during which the sun's activity grows from minimum to maximum and back. During maximum periods, when there are many sunspots, CMEs can occur several times a day. During minimum, just a few per month. 2025 is in the growth phase of the 25th solar cycle, which began in 2019. This means that coronal mass ejections during this period are not uncommon, but most of them just fly off into space, encountering nothing special on their path. They dissipate in interplanetary space, merging with the solar wind, a constant stream of particles that the sun emits in all directions. Only rarely does a CME hit Earth, causing geomagnetic storms and beautiful auroras. Even more rarely do they hit other planets or comets. And for one to hit an interstellar comet precisely, that's a coincidence that can be called a cosmic miracle. On October 22nd, 2025, this miracle happened. The cloud of plasma that burst from the solar corona began its journey through the inner solar system. Its front, the leading edge, where the concentration of particles is highest, moved at a speed of 900 kilometers per second. That's almost 3 times faster than the normal solar wind, which moves at about 400 kilometers per second. Behind the front stretched a plume of less dense plasma, magnetic loops, and turbulent structures. This entire cloud was tens of millions of kilometers in size. Inside it, the magnetic field was twisted into a spiral, creating what's called a magnetic cloud, a structure with a very orderly but heavily distorted field. When such a cloud reaches a planet with a magnetosphere, it can compress it, push through it, cause powerful currents in the upper layers of the atmosphere. For Earth, this means auroras that can be visible even at mid-latitudes and possible disruptions in electronics. But for a comet without a magnetic shield, the consequences will be completely different. While the plasma cloud moved toward Comet 3I Atlas, astronomers around the world began preparing their instruments. SOHO, the Solar and Heliospheric Observatory, located at the Lagrange point between Earth and the Sun, directed its coronagraphs at the region from which the CME burst. A coronagraph is a special telescope that blocks the sun's bright disk, allowing you to see the faint corona and objects near it. It was with the help of the LASCO coronagraphs aboard SOHO that thousands of comets were discovered, accidentally flying near our star. Many of them were suicide comets, sun-grazer comets, that flew so close to the sun that they completely evaporated or were destroyed by tidal forces. Some crashed into the sun, creating bright flashes upon impact. But 3I Atlas was at a safe distance. Its perihelion, the closest point to the sun, was at approximately the distance of Venus's orbit. It won't be destroyed by proximity to the star, but will receive enough energy to demonstrate activity. GOES 19, which first detected the ejection, continued monitoring. This satellite, launched to observe weather and space weather, has instruments for detecting the sun's X-ray and ultraviolet radiation. It's in these ranges that processes in the corona are visible that are invisible to the human eye. When a CME leaves the sun, it creates a shock wave in the solar wind, compressing the plasma ahead of it. This shock wave can accelerate charged particles to near-light speeds, creating streams of high-energy protons and electrons, solar cosmic rays, dangerous for astronauts and satellites. GOES 19 detects these particles, allowing predictions of how dangerous an ejection will be for technology in space. In the case of the October 22nd CME, the intensity was moderate, powerful enough to create impressive effects when interacting with the comet, but not strong enough to pose a threat even to satellites if it were heading toward Earth. Radio telescopes also joined the observations. When charged particles interact with gas in a comet's coma, they can generate radio emissions, low-frequency waves that propagate through space. These waves carry information about plasma density, about the strength of magnetic fields, about the chemical composition of gases. Observatories in different countries tuned their antennas to frequencies corresponding to the expected emissions. Some of them work in the meter range, picking up long waves generated by plasma oscillations. Others, at shorter wavelengths, detecting radiation from accelerated electrons. All of this together should give a picture of what's happening 150 million kilometers from Earth, in a region of space where an interstellar visitor meets the fury of our sun. And this encounter should happen in 2 days, on October 24th, 2025, when the front of the coronal mass ejection reaches the comet's orbit. But what do we know about the comet itself? 3I Atlas remains a mystery in many respects. Since its discovery on July 1st, 2025, only a few months have passed. Too little time to collect comprehensive data. It's known that its orbit is hyperbolic, with an eccentricity greater than 1, which mathematically means it's not bound by gravity to the sun, and after passing perihelion will leave our system forever, returning to interstellar space. The speed at which it entered the solar system is about 30 kilometers per second relative to the sun, too high to be captured by our star. This is the speed of an object traveling between stars. Where did it come from? Precise calculations show that the trajectory of 3I Atlas doesn't point to any specific star in our vicinity. It arrived from somewhere in the general direction of the constellation Sagittarius, but millions of years of drifting in the galaxy have erased traces of its homeland. Perhaps it was ejected from the planetary system of some star that is now hundreds of light years away. Perhaps it's older than our solar system, an ancient fragment of a protoplanetary disk that never assembled into a planet. The comet's green coma, which so attracted astronomers' attention, indicates the presence of dicarbon molecules, C2, a substance consisting of 2 carbon atoms. When solar ultraviolet hits these molecules, they transition to an excited state and then emit light at a wavelength of 510 nanometers, which corresponds to green color. This is a common phenomenon for comets, but the intensity of the glow in 3I Atlas turned out to be above average. Some researchers suggested that interstellar comets may have a higher concentration of carbon compounds than comets born in our solar system. This could be related to formation conditions in a different protoplanetary nebula, where the ratio of elements was different, or perhaps the long millions of years in interstellar space, where the comet was exposed to galactic cosmic rays, changed its chemical composition. Answers to these questions can only be provided by detailed spectroscopic observations, which are still limited by the comet's position in the sky and its brightness. The elongated shape of the nucleus is another interesting detail. The first interstellar comet, Oumuamua, discovered in 2017, also had a highly elongated shape, which sparked many discussions and even speculation about its nature. Some scientists suggested that Oumuamua might be a fragment of a destroyed planet, a kind of interstellar iceberg. Others expressed more exotic ideas, up to versions about artificial origin, although these hypotheses didn't find serious scientific support. 3I Atlas, according to preliminary data, is also elongated, with an axis ratio of approximately 3:1. This could be the result of long drift in microgravity conditions, where even weak tidal forces from passing stars gradually stretched the object. Or it's a consequence of collisions in dense regions of the protoplanetary disk where the comet was born. We don't know for sure yet, but each new detail brings us closer to understanding how planetary systems form beyond ours, what processes occur there, and how universal the laws of cosmic evolution are. Imagine the moment of impact. A cloud of magnetized plasma, heated to 1,000,000 degrees, moving at a speed of 900 kilometers per second, crashes into the rarefied atmosphere of a comet, an object whose surface temperature barely reaches -150 degrees Celsius. This is a meeting of fire and ice in the most cosmic sense of these words. But in space, there are no explosions with fire and smoke as we know them. Here, everything happens differently, more subtly, but no less dramatically. First in the path of the coronal mass ejection will be the ion tail of Comet 3I Atlas, that very ghostly plume of ionized molecules that stretches millions of kilometers away from the sun. This tail is already now, before the collision, under constant influence from the normal solar wind. Solar wind particles ionize gas molecules evaporating from the comet's surface, water vapor, carbon dioxide, carbon monoxide, cyanogen groups, and blow them away, creating a glowing tail. But when the CME arrives, the intensity of the impact will increase tenfold, possibly 100-fold. The front of the coronal mass ejection is a shock wave, a sharp boundary where particle density, magnetic field, and temperature jump dramatically. When this shock wave reaches the comet's ion tail, it will begin to compress it, condense it. The magnetic fields of the CME, twisted into complex spirals, will begin to interact with the tail's own magnetic structures. In the rarefied plasma of the comet's tail, there are weak currents and magnetic fields induced by interaction with the solar wind. When the powerful magnetic field of the ejection crashes into these structures, magnetic reconnection will occur, a process in which magnetic lines break and reconnect, releasing enormous amounts of energy. This energy will go toward accelerating particles, heating plasma, and generating electromagnetic waves. The ion tail will begin to glow brighter, possibly changing color, as different molecules transition to excited states. The bluish glow of ionized carbon monoxide may give way to greenish tones from excited oxygen, reddish from hydrogen. This will be a cosmic fireworks display, visible only to special instruments, but no less impressive for it. Then that very tail disconnection event will occur, which scientists talk about with such interest. The magnetic pressure from the CME may be so strong that it will literally tear the ion tail from the comet's coma. The boundary between the coma and tail, where magnetic fields usually smoothly transition into each other, will abruptly rupture. The tail will begin to drift into space as a separate structure, carrying away millions of tons of ionized gas. The comet will briefly be left without a tail, only with its coma and dust tail, which is less sensitive to magnetic fields. But evaporation from the nucleus surface continues constantly. Solar radiation continues to heat the ice, gases continue to emerge, ionize, and be carried away by the solar wind. Within just a few hours or days, the comet will begin to form a new ion tail, possibly at a different angle, with a different structure, because the magnetic fields in space will have changed after the CME's passage. Astronomers have observed such events in comets before. Comet Encke, one of the most famous short-period comets, regularly loses its tail when passing through boundaries of interplanetary magnetic field sectors. But the impact of the coronal mass ejection won't be limited to just the tail. Part of the CME's energy will reach the coma itself, the gaseous envelope around the comet's nucleus. The coma of 3I Atlas extends hundreds of thousands of kilometers. It's an enormous but very rarefied cloud of molecules and dust particles. When high-energy particles from the ejection begin crashing into this cloud, they'll transfer their energy to gas molecules. The process is called excitation. Electrons in atoms and molecules transition to higher energy levels. Then, returning to their original states, emit photons. This is fluorescence, the glow that makes comets visible. Usually this glow is caused by solar ultraviolet, but during the CME's passage, additional energy sources will be added, plasma particles accelerated by magnetic fields. The coma's brightness may increase several times over. The green glow of dicarbon will intensify, and perhaps lines of other elements will become visible: sodium, calcium, iron, if they're present in the comet's composition. Spectroscopy, the method of analyzing light by breaking it down into different wavelengths, will allow scientists to determine exactly what substances are in the comet, in what quantities, in what state. Another effect that may occur is enhanced sublimation from the nucleus surface. Sublimation is the transition of a substance from solid state directly to gaseous, bypassing the liquid phase. In the vacuum of space, this is the primary method of evaporation. Ice on the surface of the comet's nucleus is heated by sunlight. Molecules gain enough energy to break away from the surface and fly off into space. Usually, this process is slow, but when additional energy from charged particles in the CME begins bombarding the surface, the sublimation rate may sharply increase. The comet's nucleus will begin ejecting more gas, more dust. The comet's activity will intensify. It may become brighter even for ground-based observers, if not for the solar conjunction that makes observations from Earth nearly impossible. Nevertheless, spacecraft will record this change. An increase in gas flow means an increase in the mass the comet is losing. For a small object, which the nucleus of 3I Atlas is, probably several kilometers in diameter, this could be a significant loss. Each passage near the Sun decreases the comet's mass, and if you add the impact of a powerful CME, the process accelerates. Interestingly, comets are a kind of time machine. The material they're made of formed billions of years ago, in the era when planetary systems were born. In our solar system, comets from the Oort cloud and Kuiper belt preserve pristine material from the protosolar nebula, that very nebula of gas and dust that 4.5 billion years ago compressed, forming the Sun and planets. Comets have hardly changed during this time, because they were far from the Sun, in cold and darkness, where no processes could transform their material. When a comet first enters the inner solar system, scientists get a chance to study material that remembers the era of planet formation. Interstellar comets, like 3I Atlas, carry even more valuable information. They preserve material from another protoplanetary system, possibly from another era, another region of the galaxy. Studying their composition gives us a window into the diversity of conditions for planet formation in the universe. And when such a comet undergoes extreme impact, as in the case of collision with a CME, it provides an additional opportunity to understand how cometary material reacts to high-energy processes, what chemical reactions can occur, which molecules break down, and which form. Some researchers have hypothesized that comets may have played a role in the origin of life on Earth. Billions of years ago, when our planet was just forming, an enormous number of comets and asteroids fell on it. This bombardment brought water to Earth. Most of the water in our oceans possibly has cometary origin, but not just water. Comets contain organic molecules, amino acids, sugars, nucleotide bases, the building blocks of life. When comets fell on early Earth, they delivered these molecules, enriching the chemical composition of the young planet. Of course, this is just a hypothesis, one of many explaining the origin of life, but it has serious scientific support. Analysis of comet material shows the presence of complex organic compounds that could have become precursors to biological molecules. If interstellar comets, like 3I Atlas, also contain organics, and there's every reason to believe they do, this means that the building blocks of life are widespread not only in our solar system, but throughout the galaxy. Life can arise wherever there are suitable conditions, because the necessary ingredients are delivered by comets from interstellar space. But let's return to the physics of the collision. Besides visible and spectroscopic effects, the interaction of the CME with the comet will generate radio emission. When charged particles are accelerated in magnetic fields, they emit electromagnetic waves. This process is called synchrotron radiation if the particles are moving at near light speeds, or cyclotron radiation if the speeds are lower. Additionally, plasma oscillations arise, waves in the plasma itself, which can also generate radio waves. These waves propagate through interplanetary space and can be received by radio telescopes on Earth or in orbit. By analyzing the frequency, intensity, and polarization of radio emission, scientists can reconstruct the picture of processes at the collision site, what the plasma density is, how strong the magnetic fields are, how fast the particles are moving. It's like listening to distant music and determining from its sound what instruments are playing, what the melody is, at what tempo. Except instead of music, radio waves, and instead of instruments, physical processes in cosmic plasma. Scientists also expect to see changes in the X-ray range. When high-energy electrons decelerate in matter or magnetic fields, they emit X-rays. Comets are usually weak sources of X-ray emission, but during interaction with a powerful stream of particles from a CME, their X-ray brightness can increase. Space X-ray telescopes, such as Chandra or XMM Newton, could observe this if the comet were in a suitable position and if they were allocated observation time. Unfortunately, solar conjunction makes it difficult to point many instruments, but some data may still be collected. Each photon, each particle detected by sensors adds a piece to the enormous mosaic of our understanding of the cosmos, and the event of October 24, 2025, will become one of the brightest pieces of this mosaic, a unique case where nature itself set up an experiment that we couldn't conduct artificially. To understand just how unique Comet 3I Atlas is, we need to go back in time and trace the history of interstellar object discoveries. For decades, Astronomers assume that wanderers must exist between stars, comets, asteroids, planetary fragments ejected from their home systems by gravitational disturbances. Theoretical calculations showed that in each planetary system during its formation, billions of objects are ejected into interstellar space. Young giant planets with their powerful gravity catapult small bodies away, sending them on an eternal journey through the galaxy. Our solar system is no exception. Over 4.5 billion years of existence, we've ejected trillions of objects into interstellar space. It was logical to assume that other systems do the same, filling the galaxy with these cosmic refugees. But finding them turned out to be incredibly difficult. Interstellar space is enormous. Objects move quickly and don't emit light themselves. They can only be seen when they reflect a star's light. We needed luck for such an object to fly close enough to the sun for our telescopes to spot it. That luck came on October 19, 2017, when the Pan-STARRS telescope in Hawaii discovered a strange object moving on an unusual trajectory. At first, it was taken for an ordinary comet or asteroid, but when astronomers calculated the orbit, they froze in amazement. The orbital eccentricity was about 1.2. This meant the object was moving on a hyperbola. It wasn't gravitationally bound to the sun, and after passing perihelion, would leave the solar system forever. The velocity relative to the sun was too high for any object born in our system. This was the first confirmed interstellar visitor. It was named Oumuamua, which in Hawaiian means scout or messenger from afar. The name was perfect for an object that came from beyond our cosmic home. Oumuamua swept through the inner solar system and began moving away before scientists could gather enough data. But even the little that was learned raised many questions. The object had an extremely elongated shape with a length-to-width ratio of 10:1, like a cosmic cigar or pancake, depending on data interpretation. It rotated around its axis, creating brightness fluctuations. And strangest of all, it showed slight acceleration, not explainable by gravity alone. This acceleration sparked heated debates. Comets usually accelerate due to a reactive effect. When gas evaporates from the surface, it creates thrust, like a small rocket engine. But Oumuamua had no visible coma or tail, no signs of evaporation. Some scientists suggested it was still releasing gas, just too weakly to notice. Others proposed the idea that the object might be very light, almost like a sponge, and sunlight pressure creates enough force to accelerate it. There were more exotic hypotheses too. For example, that Oumuamua might be a fragment of an artificial structure, a solar sail from an alien civilization, lost or abandoned. This idea, put forward by astronomer Avi Loeb from Harvard, generated enormous public interest, though most scientists were skeptical. Too many ordinary explanations remained unexplored to jump to conclusions about aliens. But the very fact that such discussions were happening showed how unusual Oumuamua was and how little we knew about interstellar objects. It left as suddenly as it appeared, leaving behind more questions than answers. The second interstellar visitor arrived on August 30th, 2019. Gennady Borisov, an amateur astronomer from Crimea, discovered a comet using a homemade telescope. When professional astronomers confirmed the discovery and calculated the orbit, it became clear. This was the second interstellar object. It was named 2I Borisov, in honor of its discoverer, where 2I means second interstellar. Unlike the mysterious Oumuamua, Comet Borisov behaved like a real comet. It had a bright coma, dust and ion tails. It was actively evaporating, ejecting gas and dust. Spectroscopic observations showed the presence of water, carbon dioxide, cyanogen, ordinary cometary substances. In chemical composition, Comet Borisov was surprisingly similar to comets in our solar system. This was a crucial result. It showed that comet formation conditions in other star systems could be similar to ours, that chemical processes in the universe are universal. Astronomers around the world pointed their telescopes at the comet, collecting data. The Hubble Space Telescope made detailed images showing the structure of the coma and tail. Ground-based observatories conducted spectroscopy, analyzing composition. Over several months of observations, more information was gathered than during all the brief time of Oumuamua's existence. Comet Borisov passed perihelion on December 8, 2019, at a distance of about 2 astronomical units from the Sun, roughly where Mars's orbit is. Then it began moving away, gradually dimming until it became too faint for observations. But the data collected during its visit gave scientists an enormous amount of information. It was confirmed that interstellar comets exist in large numbers. Statistical calculations showed that several interstellar objects pass through the inner solar system every year. It's just that most of them are too small or too dim to notice. With telescope development, with the launch of new survey programs, the number of discoveries should grow. And indeed, on July 1, 2025, the Atlas system in Chile discovered the third confirmed interstellar object, Comet 3I Atlas. The third wanderer from the interstellar abyss, the third messenger from distant star systems. And this time, fate arranged it so that its visit coincided with a powerful coronal mass ejection, creating a unique opportunity for observations. The Atlas telescope system, Asteroid Terrestrial Impact, Last Alert System, was created to search for asteroids that could threaten Earth. 4 telescopes located in Hawaii, Chile, South Africa, and other places automatically scan the sky every night, photographing the same areas multiple times. A computer program compares images, looks for objects that have shifted relative to stars. These could be asteroids, comets, variable stars, supernova flashes. Over years of operation, Atlas has discovered hundreds of new asteroids, several comets, and made an enormous contribution to planetary defense. And on July 1, 2025, one of its telescopes in Chile detected a new moving object with a coma. Initial data didn't indicate anything special, but when astronomers obtained more observations and calculated the orbit, it became clear. Eccentricity greater than 1, velocity too high. Another interstellar visitor. The news spread quickly through the astronomical community, and an observation campaign began that continues to this day. Over the past months, Comet 3I Atlas has traveled a significant portion of its path toward the Sun. Its brightness increased as it approached, though it never became an object visible to the naked eye. Too far, too small. But for telescopes, it represented an excellent target. Spectroscopy showed a rich spectrum of emission lines, signs of various molecules in the coma. Dicarbon, which gives the comet its green color, was present in large quantities. Lines of cyanogen, hydroxyl, and sodium were also detected. The ratio of different elements and molecules provided information about the temperature and chemical composition of the protoplanetary disk in which the comet was born. Some preliminary results indicated slight differences from solar system comets. For example, a somewhat different ratio of hydrogen and deuterium isotopes. This could mean that water in Comet 3I Atlas formed under conditions different from those in our protosolar nebula. Perhaps the parent star was cooler or hotter than our Sun. Perhaps the disk in which the comet formed had a different chemical composition due to previous generations of stars that enriched the surrounding space with heavy elements. Each detail helped reconstruct the history of this ancient object. The elongated shape of the comet's nucleus also became an object of study. Photometric observations, brightness measurements over time, showed periodic fluctuations with a period of about 8 hours. This meant the nucleus rotates around its axis with this period, and due to the elongated shape, we see sometimes the wider, sometimes the narrower side. The amplitude of fluctuations allowed estimation of the axis ratio, approximately 3:1. Not as extreme as Oumuamua, but still noticeably elongated. Why do interstellar objects tend to have such a shape? One hypothesis relates to tidal forces. When an object passes close to a massive body, a giant planet or star, gravitational forces on the near side are stronger than on the far side. This difference can stretch the object, especially if it hasn't completely solidified yet. Over millions of years of multiple close approaches, the shape can become increasingly elongated. Another hypothesis relates to the accretion process in the protoplanetary disk. When small bodies collide and stick together, forming larger objects, collisions may not be perfectly symmetrical, creating elongated structures. There's no definitive answer yet, but each new discovery brings us closer to understanding. And now, in October 2025, Comet 3I Atlas found itself in solar conjunction, hidden by the bright light of our star from the eyes of most telescopes. Only the GOES 19 satellite and coronagraphs aboard SOHO could observe it. And at precisely this moment, a coronal mass ejection occurred, directed exactly at the comet. A coincidence that some might call chance, and others, a sign of fate. For scientists, this was a unique opportunity, a gift from nature. On October 24, 2025, humanity will witness an event it has never before observed in such detail, and every collected photon of light, every detected particle will add a new page to our cosmic encyclopedia, help us better understand this vast universe of which we are a part. On the night of October 22, 2025, when the plasma cloud tore away from the solar corona and began its journey toward the comet, preparations began worldwide among those who would observe this event. Astronomers, solar plasma physicists, spacecraft engineers, all understood that they faced a unique opportunity that might not repeat itself for decades. But observing the collision wasn't easy. Comet 3I Atlas was in solar conjunction, on the same line as the Sun when viewed from Earth. This meant that the bright light of our star eclipsed everything nearby. Most ground-based telescopes were powerless. Pointing them at the comet meant pointing directly at the Sun, which could damage sensitive instruments and provide no information beyond blinding light. Only spacecraft remained, positioned correctly with the right instruments, and chief among them was the GOES 19 satellite, which by chance turned out to be the only one that could continuously observe the comet during these critical days. GOES 19 is a geostationary satellite launched by the U.S. National Oceanic and Atmospheric Administration to monitor weather. It's located at an altitude of 36,000 kilometers above the equator, constantly hanging over one point on Earth, observing clouds, hurricanes, thunderstorms. But in addition to meteorological instruments, it has equipment on board for observing space weather, solar flares, coronal mass ejections, streams of charged particles. These instruments include X-ray and ultraviolet sensors, magnetometers, and particle detectors. When a flare or ejection occurs on the Sun, GOES 19 registers it within minutes, sending data to space weather centers, which then issue warnings to satellite operators, airlines, and power companies. And this time, its position allowed observation not only of the Sun, but also of the region of space where the comet was located. When the coronal mass ejection occurred, GOES 19 sensors detected a sharp spike in X-ray emission, a characteristic sign of solar activity. Then tracking of the plasma cloud's trajectory began. The second crucial instrument is the SOHO Observatory, the Solar and Heliospheric Observatory, a joint project of the European Space Agency and NASA. This spacecraft was launched in 1995 and has since continuously observed the Sun from the L1 Lagrange point, a special point in space located between Earth and the Sun, where gravitational forces are balanced. SOHO has 12 scientific instruments on board, but for observing the comet and coronal mass ejection, the most important are the LASCO coronagraphs, large angle and spectrometric coronagraph. A coronagraph is a telescope with a special disk that blocks the Sun's bright disk, allowing the faint corona and nearby objects to be seen. LASCO has 3 coronagraphs with different fields of view, covering the area from 1.5 to 30 solar radii. When a coronal mass ejection leaves the Sun, the coronagraphs see it as a bright expanding cloud bursting from the corona. Over nearly 30 years of operation, SOHO has recorded thousands of ejections, creating an enormous database for studying solar activity. And during these days, all 3 LASCO coronagraphs were directed at tracking the cloud moving toward Comet 3I Atlas. But SOHO is known not only for studying the Sun. By chance, it became the greatest comet hunter in history. Over years of operation, its coronagraphs discovered more than 4,000 comets, more than all of humanity's astronomers throughout all previous history combined. Most of these comets are small objects from the Kreutz family, suicide comets that fly so close to the Sun they evaporate completely. They appear in coronagraph images as small, bright points moving toward the Sun, then disappear, burning up in the solar heat. These comets are fragments of one large comet that broke apart centuries or millennia ago, and now its fragments continue to fall into the Sun. Observing them helped scientists understand comet destruction processes, the dynamics of small body movement in the inner solar system. And now the same instruments that discovered thousands of dying comets would observe how an interstellar comet experiences collision with a solar storm. This was poetic symmetry. An instrument that had seen so many deaths would now witness a unique interaction that wouldn't destroy the comet, but would change it. Radio telescopes on Earth were also preparing for observations. Although the comet was hidden behind sunlight in the visible range, radio waves could penetrate this obstacle. When the coronal mass ejection plasma interacts with the comet's coma, radio emissions arise, low-frequency waves generated by plasma oscillations and the movement of charged particles in magnetic fields. These waves propagate through interplanetary space and can be received by sensitive antennas. Observatories around the world, from the giant Arecibo radio telescope while it was still functioning, to the LOFAR systems in Europe and antenna arrays in Australia, tuned to corresponding frequencies. Each observatory had its peculiarities. LOFAR, the low-frequency array, consisting of thousands of small antennas scattered across Europe, specializes in low frequencies, from 10 to 200 megahertz. It's in this range that the most intense emissions from the CME-Comet interaction were expected. The Australian Murchison Wide Field Array Radio Telescope, located in a desert area with minimal radio interference, could detect weak signals that would be lost in the noise of cities. Some observers used more exotic methods. Interplanetary spacecraft located in different parts of the solar system could serve as additional observation points. Parker Solar Probe, a probe that regularly dives into the solar corona studying it from within, wasn't in an ideal position at this moment, but its particle sensors could still detect changes in the solar wind caused by the ejection's passage. Solar Orbiter, a European-American mission studying the Sun from close range at different angles, also contributed. Even spacecraft intended for completely different purposes, for example, Martian orbital stations, could provide indirect data by detecting disturbances in the interplanetary medium. All of this together created an observation network covering a huge area of space. This was humanity's collective work. Scientists from dozens of countries, speaking different languages, working in different institutions, but united by a common goal: to understand this unique event. While instruments prepared, more informal discussions also began. On the internet, on amateur astronomy forums, on social media, debates flared up. Some saw in the coincidence of the coronal mass ejection and the interstellar comet something more than just chance. Theories appeared that Comet 3I Atlas might not just be a chunk of ice and rock, but something more mysterious. Perhaps it carries a message from another civilization. Perhaps the coronal mass ejection was somehow provoked by the comet itself, by its fields or radiation. Of course, these ideas had no scientific basis, but they reflected the eternal human desire to find meaning in cosmic events, to see patterns where perhaps there are none. History is full of examples where comets were considered omens. From Halley's Comet, whose appearance was linked to the fall of kingdoms, to the Great Comet of 1997 Hale-Bopp, which spawned numerous rumors and even tragic events. Comets have always stirred human imagination because they come from darkness, shine in the sky, and then depart into the unknown. And an interstellar comet, a visitor from another star system. This is an even more powerful symbol. It's literally a messenger from another world, from places we can never visit, that we can only study from afar. But if we set aside mystical interpretations, the event itself remained impressive from a purely scientific standpoint. For the first time in human history, we could observe direct interaction of a solar storm with an interstellar object. Yes, we've seen how coronal mass ejections affect planets, Earth, Mars, even distant gas giants. Yes, we've observed solar wind interaction with comets from our system, but never before had these two phenomena combined in such a unique context. The data to be collected will help answer fundamental questions. How does interstellar matter, formed in another protoplanetary nebula, react to our sun's influence? Are there differences in chemical composition, in physical properties, that can be revealed through such interaction? How do the magnetic fields of a coronal mass ejection restructure the structure of the comet's coma and tail? What particle acceleration processes occur at the boundary between CME plasma and comet gases? Each of these questions could become the subject of dozens of scientific papers, dissertations, conferences. And here they all converged in one event. The anticipation of collision created a special atmosphere in the scientific community. It was similar to those moments when astronomers awaited the collision of Comet Shoemaker-Levy 9 with Jupiter in 1994. Back then, the comet, torn into more than 20 fragments by Jupiter's tidal forces, crashed into the gas giant's atmosphere, creating gigantic explosions visible even in amateur telescopes. Each fragment left a dark spot on Jupiter's surface the size of Earth. It was a spectacle observed by millions of people worldwide. The collision of the coronal mass ejection with Comet 3I Atlas would be less visually dramatic. No explosions, no fireballs. But for scientists, this was an equally important event, perhaps even more important, because it provided information about processes we understand much less well. On October 24, 2025, the eyes of all these instruments would be directed at one point in space, where ancient ice from another star system would meet the fury of our sun. Throughout all of human history, comets have inspired awe, fear, and reverence. Long before we understood their nature, these glowing wanderers in the sky seemed like messages from the gods, omens of great events, signs of changes to come. In ancient China, astronomers carefully recorded comet appearances, linking them to the fates of dynasties. A bright comet in the sky could mean the death of an emperor, the start of war, the onset of famine. Chinese chronicles contain records of comets dating back more than 2,000 years. These are among the most ancient astronomical observations that have survived to us. In medieval Europe, comets were also considered bad omens. When Halley's Comet appeared in 1066, shortly before the Norman conquest of England, its image was embroidered on the famous Bayeux Tapestry, a textile canvas depicting the Battle of Hastings. The comet is shown there as an ominous symbol, foretelling the fall of King Harold and the victory of William the Conqueror. People saw in comets the hand of fate, an inexorable force before which kings and generals were powerless. But there were also those who tried to understand comets rationally. The ancient Greek philosopher Aristotle in the 4th century BCE suggested that comets were atmospheric phenomena, something like burning gases in the upper layers of air. This theory, though incorrect, dominated European science for nearly 2,000 years. Only in the 16th century did Danish astronomer Tycho Brahe, observing a bright comet in 1577, manage to prove that comets are far beyond Earth's atmosphere. He used the parallax method, observing the comet from different places at different times. He showed that its position relative to stars didn't change as it should have if it were close to Earth. This meant the comet was in space, possibly even beyond the moon. This discovery shocked the scientific world of that time because it destroyed the Aristotelian notion of the immutability of the heavens. If comets move through space, then the heavens aren't frozen and eternal, but dynamic and changeable. This was one of the steps toward the scientific revolution that ultimately led to our modern understanding of the universe. The next major breakthrough came in the 17th century, when Isaac Newton applied his laws of motion and gravity to comets. He showed that comets move in orbits around the sun, obeying the same laws as planets. Edmund Halley, Newton's friend and colleague, went further. He collected data on comet observations over centuries and noticed that comets appearing in 1531, 1607, and 1682 had very similar orbits. Halley proposed that this was the same comet, returning every 75 to 76 years. He predicted the comet would return in 1758. Halley didn't live to see this moment. He died in 1742, but in 1758, the comet did indeed return, exactly as he predicted. This was a triumph of science, proof that the laws of nature are universal and predictable. The comet was named after Halley, though he himself never called it by his own name. Since then, Halley's Comet has returned regularly. It was last visible in 1986, with the next appearance expected in 2061. In the 19th century, understanding of comet nature deepened. Scientists realized that comets consist of ice and dust, that their tails form under the influence of solar radiation and light pressure. German astronomer Friedrich Bessel, in 1835, suggested that comet tails always point away from the sun due to some repulsive force. Later, it became clear that this force is the solar wind, a stream of charged particles from the sun. In the 20th century, with the development of space technology, we could study comets up close. Space probes flew past comets, photographed their nuclei, analyzed gas composition in the coma. The Giotto mission, launched by the European Space Agency in 1985, flew just 600 kilometers from Halley's Comet nucleus, taking the first detailed images of a comet nucleus. It turned out to look like a dark, irregularly shaped potato, about 15 kilometers long, covered with a crust of dark organic material. When sunlight heats this crust, the ice beneath evaporates, bursting through cracks and creating jets of gas and dust. But where do comets come from? This question occupied astronomers for decades. In the mid-20th century, Dutch astronomer Jan Oort proposed that far beyond Pluto's orbit, at distances of tens of thousands of astronomical units from the Sun, there exists a huge cloud of icy objects, remnants from the solar system's formation. This cloud, named the Oort cloud, contains trillions of comets that drift in an almost motionless state at the very edge of the Sun's gravitational influence. Sometimes, the gravity of a passing star or gravitational disturbances from massive molecular clouds in the galaxy slightly nudge one of these comets, and it begins falling toward the inner solar system. The journey can take millions of years, but eventually, the comet passes near the Sun, becomes visible from Earth, and then either returns to the Oort cloud, or, if its orbit changed from the gravitational influence of planets, remains in the inner system as a short-period comet. The Oort cloud has never been directly observed. Objects there are too small and distant to see. But indirect evidence, such as the orbits of long-period comets, convincingly points to its existence. Besides the Oort cloud, there's the Kuiper belt, a region beyond Neptune's orbit where millions of icy objects are located. Pluto, once considered the 9th planet, is now classified as one of the largest Kuiper belt objects. Short-period comets, like Halley's Comet, probably originate from this belt. They were ejected from the Kuiper belt by Neptune's gravity or other planets, and now orbit the Sun with periods from several years to 200 years. Studying these objects provides information about the early solar system, about processes that occurred 4.5 billion years ago when planets were just forming. But if comets in our system preserve the history of our past, then interstellar comets, like 3I Atlas, preserve histories of other worlds, other stars, other planetary systems. Each such comet is a message from the depths of the galaxy, written in the language of atoms and molecules, which we're only learning to read. Now, knowing all this, we can appreciate how unique the situation with Comet 3I Atlas is. It was born not in our solar system, but somewhere far away, possibly in a planetary system around a star hundreds of light years from us. Maybe it was a star similar to our Sun, a yellow dwarf surrounded by planets. Maybe a cooler red dwarf, the most common type of star in the galaxy. Or perhaps a hotter and more massive star, living faster and brighter. We don't know. Millions or billions of years ago, something happened in that system. Maybe young giant planets migrated, changing orbits and with their gravity ejecting thousands of small bodies into interstellar space. Maybe another star passed nearby, and its gravity disturbed the cloud of comets around the parent star. Either way, the comet we now call 3I Atlas was sent on a long journey through the void between stars. For millions of years, it drifted in absolute darkness and cold, at temperatures just a few degrees above absolute zero. No light, no heat, only rare atoms of interstellar gas and cosmic rays, high-energy particles permeating the galaxy. Over these millions of years, cosmic rays slowly changed the comet's surface. They knocked atoms out of the ice's crystalline lattice, created new molecules, destroyed old ones. Perhaps they created a layer of modified material, different in composition from the deep layers that remained untouched since formation. This layer, called a cosmic crust or regolith, may preserve information about time spent in interstellar space. If we could send a probe to Comet 3I Atlas, take samples of material and study them in a laboratory, we could learn how much time it spent traveling, through which regions of the galaxy it passed, what radiation it was exposed to. but such missions remain beyond our technological capabilities for now. Interstellar objects move too fast, and we don't have rockets capable of catching them. All we can do is observe from afar, collect light, analyze spectra, build models and hypotheses, and wait for unique events like collision with a coronal mass ejection that provide additional opportunities for study. Among those following Comet 3I Atlas with special interest were not only scientists. On the internet, on forums dedicated to the unexplained and conspiracy theories, heated discussions unfolded. Some claimed the comet's shape was too regular to be natural, that it might be an artificial object, a spaceship or probe from an alien civilization. These ideas echoed debates around Oumuamua when its unusual elongated shape and strange acceleration spawned similar speculation. Others saw in the coincidence of the coronal mass ejection and the comet's passage some deliberate message, an attempt at contact. Maybe the comet was intentionally directed toward our sun, knowing that such an event would attract the attention of any intelligent civilization in the system? Of course, from a scientific standpoint, these theories didn't withstand scrutiny. Too many unfounded assumptions, too little evidence. But they reflected a deep human desire not to be alone in the universe, to find signs of other intelligent beings, to make contact with something greater than ourselves. The truth, however, was probably simpler and simultaneously more amazing. Comet 3I Atlas is a piece of ancient ice, a fragment of a planetary system that perhaps ceased to exist long ago. Maybe its parent star already died, turning into a white dwarf or exploding as a supernova. Maybe the planets of that system were long ago swallowed by an expanding star or destroyed by collisions. And this small piece of ice continues to exist, carrying within itself the last traces of what once was. This is simultaneously sad and beautiful. The thought that we may be the only ones who remember this long-vanished system, the only ones studying the last remnants of its material. The collision with the coronal mass ejection on October 24, 2025, will be another chapter in the long history of this object. After the collision, the comet will continue its journey, leave our solar system, and again head into interstellar space. Perhaps in millions of years it will encounter another star, another planetary system. Or maybe it will drift forever until it completely evaporates under the influence of galactic cosmic rays, dispersing into the finest dust that will become part of the interstellar medium. But for now, in these October days of 2025, it's ours. The object of our attention, our observations, our reflections on the nature of the universe, and our place in it. Between the coronal mass ejection on the night of October 22nd and the anticipated collision on October 24th, lay 2 days of waiting. This was a strange time for those following the event: astronomers, physicists, space enthusiasts around the world. The plasma cloud was already racing through space, invisible to the human eye but tracked by instruments. Its speed was about 900 kilometers per second, which means that every second it covered a distance equal to the length of almost 30 marathon courses. Every minute, 54,000 kilometers, more than Earth's circumference. Every hour, over 3 million kilometers. And all this time, Comet 3I Atlas continued its orbital motion, unsuspecting, if one can say that about an inanimate object. It continued to evaporate gases. Its coma glowed with the green light of dicarbon. Its ion tail stretched behind it for millions of kilometers. For now, it didn't sense the approaching storm. The normal solar wind, a constant stream of particles from the sun, was still the only thing affecting its fragile atmosphere. During these 2 days, scientists conducted final preparations. Telescope settings were checked, detectors calibrated, observation schedules compiled. Each observatory wanted to get its share of data. Each had its priorities and scientific goals. Some planned continuous observations for several days to capture the event's development from beginning to end. Others concentrated on specific moments, on the very collision of the ejection front with the comet, on the hours after collision when effects should be most pronounced. Modeling specialists ran computer simulations, trying to predict what exactly would happen. They input known parameters into programs: the mass and velocity of the coronal mass ejection, the density and magnetic field inside it, the size and activity of the comet, the evaporation rate of gases from its nucleus. Then, computers calculated the interaction, creating visualizations of how plasma would crash into the coma, how magnetic fields would intertwine and reconnect, how the comet's tail would deform and possibly detach. Of course, these models were simplifications of reality. Too many unknown parameters, processes in plasma too complex. But they provided a reference point, an idea of what to expect. On October 23rd, one day before the anticipated collision, the plasma cloud had already traveled more than halfway. It was somewhere between the orbits of Mercury and Venus, continuing its rapid movement. Instruments aboard SOHO tracked its progress, monitoring changes in the interplanetary medium. A coronal mass ejection isn't just a cloud of particles moving through emptiness. It's a complex structure with internal organization. At the front goes a shock wave, a boundary where the oncoming plasma compresses and heats the normal solar wind. Behind the shock wave follows a region of compressed plasma where particle density is several times higher than normal. Then comes the magnetic cloud, the central part of the ejection, where magnetic fields are twisted into a smooth spiral, creating an ordered structure amid the chaos of surrounding plasma. This central part possesses the greatest energy. Here the magnetic fields are strongest. When it reaches the comet, effects will be maximal. But the shock wave will arrive first, warning of the main event's approach. Calculations showed that the shock wave should reach the comet's orbit around morning on October 24th Moscow time, with the main magnetic cloud arriving several hours later. While the cloud approached, astronomers continued studying the comet itself, collecting final data before collision. Each spectrum, each brightness measurement added information about its state. The green coma remained stable, with no signs of sudden changes in activity. The dust tail stretched behind the comet, following its orbit, slowly curving under the action of sunlight pressure. The ion tail, more straight and narrow, pointed strictly away from the sun, governed by the magnetic fields of the solar wind. In a few hours, this picture would change. In a few hours, humanity would see what it had never seen before: a collision of worlds, a meeting of matter from different eras, different places in the galaxy. Ice formed billions of years ago in a protoplanetary disk around a distant star would meet plasma, born just 2 days ago in our sun's corona. This was a meeting of antiquity and modernity, a meeting of cold and heat, a meeting of order and chaos. In a sense, it was a collision of past and present, recorded in the language of physics and chemistry. The night from October 23rd to 24th was quiet. Most people slept, unaware of what was happening in space above their heads. But in observatories, lights burned. Duty astronomers monitored computer screens where data from spacecraft updated in real time. Graphs showed changes in solar wind density, in magnetic field strength, in charged particle flows. For now, everything remained relatively calm, normal fluctuations of the interplanetary medium, without sharp spikes. But this was the calm before the storm. Experienced space weather observers knew that when the coronal mass ejection front reached the detectors, the graphs would change dramatically. Particle density would jump several times. The magnetic field would strengthen, possibly reverse direction. Plasma temperature would increase, and all this would mean the storm had arrived. Some of these detectors were on near-Earth satellites, others on interplanetary probes scattered throughout the inner solar system. All were parts of a giant monitoring network that humanity built over decades of the space age. On the morning of October 24th, when the first rays of sun touched Earth's eastern continents, changes began occurring in space. Detectors on the GOES 19 satellite detected a sharp jump in proton flux, the first sign that the shock wave from the coronal mass ejection had reached the area where the comet was located. Graphs on computer screens shot upward. Operators in space weather centers began receiving automatic alerts. The event had begun. Over the following minutes and hours, instruments around the world and in space began registering changes. Radio telescopes caught bursts of low-frequency emission, plasma waves generated by the shock wave propagating through the interplanetary medium. SOHO coronagraphs detected changes in the brightness of the area around the comet. Though resolution was insufficient to see details, the comet appeared as just a faint point of light, barely distinguishable against the corona's background. But even this was valuable information. The brightness change meant something was happening, that energy was being transferred from the ejection to the comet, that interaction processes had been triggered. The following hours were most critical. During this time, the magnetic cloud, the central, most powerful part of the ejection, should completely envelop the comet. Imagine a small piece of ice, just a few kilometers across, surrounded by an enormous cloud of heated plasma, millions of kilometers in size. The comet's nucleus, cold and dark, suddenly found itself in an environment where temperature reached 1,000,000 degrees, where magnetic fields were thousands of times stronger than Earth's magnetic field, where charged particles rushed at speeds of tens and hundreds of kilometers per second. Of course, the impact on the solid nucleus itself was limited. Plasma is too rarefied to directly heat ice. But the comet's coma and tail, consisting of gas, were completely immersed in this environment. The ejection's magnetic fields began restructuring the ion tail's structure. Magnetic field lines that were previously relatively ordered, stretched away from the sun, began twisting, intertwining, breaking, and reconnecting. The magnetic reconnection process released enormous amounts of energy at local points, creating light flashes in different spectral ranges. If someone could observe this scene up close, protected from deadly radiation and plasma, the spectacle would be fantastic. The comet's ion tail, usually thin and straight, would begin writhing like a snake in the wind. Its brightness would fluctuate. Sections would become brighter, then dim, as waves of energy ran along the tail. Color could change, from the bluish glow of carbon monoxide to greenish tones of excited oxygen to reddish shades of the hydrogen alpha line. At some point, perhaps, a disconnection event would occur. The boundary between coma and tail would abruptly rupture, and the tail would begin drifting away, leaving the comet temporarily without this ghostly plume. But all this was happening at a distance of 100 million kilometers from Earth, hidden from direct observation by the sun's bright light. Only indirect data, changes in radio emission, fluctuations in detected particles, spectroscopic observations in moments when geometry allowed, gave an idea of what was happening at that distant point in space. The scientific significance of this event is hard to overestimate. For the first time, researchers had the opportunity to study how interstellar matter reacts to extreme conditions near our sun. Every comet is unique, but interstellar comets are even more unique. They carry chemical signatures of completely different formation conditions. If the composition of Comet 3I Atlas truly differs from solar system comets, For example, if the ratio of different isotopes is different, if molecules rare or absent in our comets are present, these differences could manifest particularly clearly during interaction with the coronal mass ejection. The additional energy transferred to the coma and tail would make molecules glow brighter, make spectral lines more pronounced, facilitate their detection and analysis. Each photon of light coming from the comet during these hours carried information about its composition, about its history, about that distant system where it was born. Spectrographs decomposed this light into components, creating rainbow spectra with dark and bright lines, each corresponding to a specific element or molecule. Beyond purely scientific interest, the event had deeper philosophical significance. It reminded us how interconnected the universe is. Here's an object born in another star system, possibly billions of years ago, meeting matter ejected by our sun just 2 days ago. Space and time compress in this encounter. Antiquity and modernity, distant and near, unite in one event. This reminded us that matter in the universe constantly circulates, transitioning from one form to another, from one place to another. The atoms in your body were once part of distant stars that exploded as supernovae, scattering their innards into space. These atoms then became part of molecular clouds from which new stars and planets formed. In a sense, we're all children of stars, created from stardust. And when we observe a comet from another star system, we see our distant relative, an object that traveled a different path, but consists of the same basic elements, governed by the same physical laws. October 24th, 2025, will enter astronomy's history as the day humanity first observed direct interaction of a solar storm with an interstellar object. The data collected on this day and subsequent days will be analyzed for months and years. Dozens, possibly hundreds of scientific papers will be published describing various aspects of the event. Graduate students will write dissertations based on this data. Conferences will gather scientists to discuss results and their interpretation. And each new detail, each new discovery will bring us closer to a deeper understanding of the cosmos. This is a slow, painstaking process. Science doesn't provide instant answers, but it's this methodicalness, this attention to detail, this willingness to reconsider hypotheses in light of new data that makes science such a powerful tool for knowledge. And events like the collision with Comet 3I Atlas are fuel for this process, providing new facts for reflection, new puzzles to solve. When the main wave of the coronal mass ejection passed through the area where Comet 3I Atlas was located, it was time to assess the consequences. The plasma cloud continued its movement farther into the depths of the solar system, gradually dispersing, dissolving into the normal solar wind. Its energy was spent, magnetic fields weakened, particles slowed. Within a few days, almost nothing remained of the once powerful ejection. Only weak disturbances in the interplanetary medium, barely distinguishable against the background of normal fluctuations. But the comet had changed. The first signs of these changes began appearing just a few hours after the peak of interaction. Spectroscopic observations showed strengthening of some emission lines, particularly sodium and calcium lines, which were barely noticeable before. This meant that the additional energy from the ejection had indeed penetrated the comet's coma, exciting atoms of these elements and making them glow brighter. The brightness of the coma itself increased by about 30% in the ultraviolet range, a significant increase, though insufficient to make the comet visible to the naked eye from Earth. But for instruments, this was a dramatic change, a clear signal that the interaction had a real impact. The comet's ion tail truly underwent a disconnection event, as the models predicted. SOHO coronagraphs captured the moment when the bright tail structure suddenly split into two parts. The proximal part, closer to the nucleus, remained connected to the coma, continuing to receive nourishment from evaporating gases. The distal part, the far end of the tail, began slowly drifting away, carrying with it millions of tons of ionized gas. This was a ghostly plume, gradually dimming as it moved away from the energy source. Within a few days, it became so faint that it ceased to be distinguishable even to the most sensitive instruments, dissolving into the interplanetary medium. Meanwhile, the comet began forming a new tail. Evaporation from the nucleus surface continued uninterrupted. Solar heat didn't stop with the end of the coronal mass ejections impact. Gases emerged, were ionized by the sun's ultraviolet radiation and normal solar wind, and gradually a new tail structure began taking shape. It formed at a slightly different angle because the magnetic fields in the interplanetary medium had changed after the ejection's passage. It was like a tree that lost old branches in a storm and now grows new ones, possibly in other directions, following new conditions. The comet nucleus's activity did indeed intensify, as expected. The ice sublimation rate increased by about 20% during the day after the interaction peak, before gradually returning to previous values. This meant that the additional energy transferred by the ejection penetrated not only the coma, but also reached the nucleus surface, albeit in weakened form. Bombardment by charged particles heated the upper ice layer, accelerating the evaporation process. The comet ejected more gas and dust than usual for its distance from the sun. This additional material enriched the coma, made the dust tail slightly brighter and denser. For a small comet nucleus, just a few kilometers in size, the loss of even several million tons of matter was noticeable. Of course, the comet didn't disintegrate. The impact was intense but not catastrophic enough to split the nucleus. But it became slightly smaller, slightly lighter. Each passage near a star diminishes comets, and this interaction with the coronal mass ejection accelerated the process. Over millions of years of such passages near various stars, the comet will gradually evaporate completely, leaving behind only a cloud of dust drifting in interstellar space. Analysis of radio data brought additional discoveries. Bursts of low-frequency emission detected at the moment of the ejection front's collision with the comet showed characteristic signs of particle acceleration. When the shock wave crashed into the coma, it created turbulence in the plasma, chaotic movements, vortices, magnetic inhomogeneities. In this turbulent environment, some charged particles received additional energy, accelerating to high speeds. This is the same process that occurs during solar flares and in supernova remnants. Particle acceleration in shock waves. Some of these accelerated particles reached low-energy cosmic rays capable of penetrating deeper into the comet's matter. They were probably responsible for the enhanced sublimation, transferring their energy to ice on the surface and in subsurface layers of the nucleus. Detailed study of the radio burst's temporal structure allowed reconstruction of the process picture, how the shock wave passed through the coma, how magnetic fields reconnected, how energy redistributed among various system components. This was complex physics, requiring comprehensive modeling and careful comparison of data with theory. Spectroscopic observations conducted in the days and weeks after the event provided information about the comet's chemical composition that would have been harder to obtain under normal conditions. The enhancement of emissions under the ejection's influence revealed the presence of several molecules and atoms that were previously at the detection limit. Besides the already mentioned sodium and calcium, lines of iron, nickel, even traces of heavier elements were detected. This indicated that the comet's composition includes not only ice, but also a rocky component with metal admixtures. The ratio of different hydrogen isotopes, ordinary hydrogen and its heavy isotope deuterium, turned out to be slightly different from the average for solar system comets. The deuterium to hydrogen ratio was 10% higher. This is a small but statistically significant difference. It indicated that water in Comet 3I Atlas formed under conditions slightly different from those in our protosolar nebula. Perhaps the parent star's protoplanetary disk had more deuterium, or the temperature was lower, which promoted the inclusion of more heavy isotope in ice grains. Each such detail was a puzzle piece helping reconstruct the history of a distant planetary system. Additionally, organic molecules were discovered. Spectra showed the presence of hydrogen cyanide, formaldehyde, methanol, simple organic compounds that are building blocks for more complex molecules. These substances are common in solar system comets, but their detection in an interstellar comet was important confirmation that organic chemistry is universal. Wherever planetary systems form, carbon compounds are present, capable under suitable conditions of evolving into more complex structures. This strengthened the panspermia hypothesis, the idea that life or its precursors can spread throughout the universe through comets and other interstellar objects. Of course, finding simple organic molecules isn't the same as finding life itself, but it shows that the necessary ingredients are widely distributed, that conditions for life's emergence may exist in many places. This is simultaneously an encouraging and humbling thought. Encouraging because it says we're probably not alone. Humbling because it emphasizes how small a part we are of an enormous universe full of possibilities. In subsequent weeks, Comet 3I Atlas continued its orbital journey. It passed perihelion, the closest point to the Sun, and began moving away. With each day, the distance to our star increased, solar radiation weakened, the comet's activity decreased, the coma became smaller and dimmer, tails shortened. The moment was approaching when the comet would begin leaving the inner solar system, returning to the cold of the outer regions. In a few months, it will cross Mars's orbit, heading toward the asteroid belt. In a year or two, it will be at Jupiter's orbital distance, then Saturn, Uranus, Neptune. Each of these milestones will mean further removal from the Sun, and at some point, possibly in a few years, Comet 3I Atlas will leave the area of the Sun's gravitational dominance and again enter interstellar space. It will carry with it traces of its visit to our star, an altered surface, reduced mass, possibly even microscopic particles of terrestrial origin captured from the solar wind or interplanetary dust. In a sense, it will become a messenger from us, a tiny trace of humanity heading into the depths of the galaxy. Astronomers will continue observing the comet as long as possible. With each month, it will become dimmer and dimmer as it recedes and activity decreases. Eventually, a moment will come when even the most powerful telescopes can't distinguish it. It will become too faint, too small, too distant. The last observation will be noted in journals, the last photograph saved in archives, and then the comet will disappear from human sight, returning to the unknown from which it came, but the data will remain. Thousands of spectra, millions of photons of light captured by detectors, radio emissions recorded on computer disks. All this will be stored, analyzed, interpreted. Decades from now, when new analysis methods appear, new theories, scientists will return to this data, extracting new information from it. Events like the collision of a coronal mass ejection with Comet 3I Atlas don't happen often. Each such event is unique, and data from it represents enormous value. Meanwhile, In the scientific community, preparation of publications began. The first papers describing preliminary observation results appeared just a few weeks after the event. They were published in special journal sections devoted to rapid communications, short works presenting basic facts without deep analysis. More detailed studies took months. Teams of scientists around the world worked on various aspects. Some analyzed spectroscopic data, trying to determine the comet's precise chemical composition. Others studied interaction dynamics, modeling plasma processes. Still others focused on long-term effects, tracking changes in the comet's brightness and activity in subsequent weeks. Each group contributed to the overall picture. This was international collaboration at its best. Scientists from different countries, cultures, speaking different languages, united by the common goal of knowledge. Political boundaries didn't matter when it came to understanding the universe. Data was freely exchanged, ideas discussed at conferences and in electronic correspondence. Collaboration flourished. For the general public, the event remained mostly unnoticed. News mentioned it in passing, if at all. Most people were busy with their daily affairs, their concerns, and the collision of a solar storm with a distant comet seemed too abstract, too far from their lives. But those interested in space, who followed astronomical news, who understood what was happening significance, felt awe. In forums and social media, they discussed details, shared speculation, built theories. Some of these theories were fantastic. Versions about alien signals, hidden messages, secret missions. Others were more down-to-earth but no less fascinating. Reflections on the comet's origin, on its parent star's fate, on the possibility of life in that distant system. These discussions, though not always scientifically rigorous, reflected the human need for stories, for narratives that give meaning to cosmic events. We want not just to know facts, we want to understand their significance, their place in the larger story of the universe and ourselves. And Comet 3I Atlas, this small piece of ice from another star system, became the hero of one such story. A story about a meeting of worlds, about a journey through the void, about the touch of antiquity and modernity in a dance of cosmic forces. The event of October 24, 2025, became a turning point in the study of interstellar objects. For the first time, humanity had the opportunity to observe not just the passage of such an object through our system, but also its interaction with solar activity in real time. This opened new horizons for science and spawned many questions about the future of research. Astronomers around the world began discussing how to prepare for the next such event, what instruments need to be developed, what observation methods to improve. Statistical models showed that interstellar objects pass through the inner solar system regularly, possibly several times a year. It's just that most of them are too small, too dim, or move at inconvenient angles to be noticed by modern telescopes. But with each year, telescopes become more powerful. Survey programs cover larger areas of sky. Data processing algorithms improve. In the near future, the number of discovered interstellar visitors should sharply increase. Perhaps in a decade, we'll be discovering dozens of such objects annually, each with its unique history, each carrying information about distant worlds. One of the most ambitious projects discussed in scientific circles was the idea of an intercept mission to an interstellar object. When Oumuamua was discovered in 2017, some enthusiasts proposed sending a space probe to it. Quick calculations showed that with existing technologies this was possible, but would require launch within a few weeks of discovery and use of multiple gravitational maneuvers around planets to gain speed. There was no time for preparation. While engineers discussed possibilities, Oumuamua was already moving away. becoming an increasingly inaccessible target. With Comet Borisov, the situation repeated. It was discovered earlier in its path, which gave more time, but still not enough to organize a full mission. Developing a spacecraft, its construction, testing, launch, all this takes years with the usual approach. By the time the probe would be ready, the comet would have already left the solar system. But these failed attempts served as a lesson. The astronomical community began discussing the concept of a rapid response probe, a spacecraft that would be built in advance, kept in a state of readiness, and could be launched within weeks of discovering a suitable target. Such a probe should be compact and light so it can be accelerated to high speeds. It should carry a minimal set of scientific instruments, a camera for photography, a spectrometer for composition analysis, possibly a mass spectrometer for studying gases in the coma if the target turns out to be a comet. The most difficult part is the energy for acceleration. Chemical rockets we use now are too slow to intercept fast-moving interstellar objects. More advanced technologies are needed. Ion engines that work for years gradually accelerating the craft, or even solar sails using sunlight pressure for acceleration. The solar sail concept is particularly intriguing. Imagine a huge, extremely thin sheet of reflective material hundreds of meters in size attached to a small probe. When sunlight hits the sail, it transfers momentum, slowly but continuously accelerating the craft. Near the sun, where light is most intense, acceleration can be significant. A probe with a solar sail could accelerate to speeds of tens of kilometers per second, enough to catch up with some interstellar objects. Several solar sail prototypes have already been tested in space, proving the concept's viability. Perhaps in coming decades, we'll see the first mission of this type. But even without sending probes, remote observations continue to improve. A new generation of telescopes promises to revolutionize the study of small solar system bodies and interstellar visitors. The Vera-Rubin telescope, also known as the Large Synoptic Survey Telescope, began its observations in the mid-2020s. This instrument in Chile is equipped with a camera with a resolution of 3 billion pixels, the largest digital camera ever built for astronomy. Every few nights it photographs the entire visible sky, creating gigantic image databases. Comparing images of the same areas taken at different times, computer programs automatically identify objects that have moved: asteroids, comets, variable stars. In a year of operation, the Rubin telescope discovers more new objects than all previous surveys combined. Among this multitude, interstellar visitors will certainly be found. By some estimates, the Rubin telescope may detect one interstellar object every month, or even more frequently. This will create the richest database for study, allow determination of how common such objects are, what typical sizes, shapes, and compositions are. The James Webb Space Telescope, launched in 2021, has also contributed to the study of interstellar objects. This infrared telescope, located at a distance of 1.5 million kilometers from Earth at the L2 Lagrange point, possesses incredible sensitivity. It can see faint objects inaccessible to other instruments and conduct detailed spectroscopy, revealing chemical composition with unprecedented accuracy. When the next interstellar object is discovered at a suitable time and in a suitable area of sky, Webb will point its mirrors at it, collecting precious photons of infrared light. This range is especially important for studying cold objects like comets, because thermal radiation from their surface falls precisely in infrared waves. Analyzing this light, scientists will be able to determine surface temperature, the presence of various ices, water, methane, ammonia, and even complex organic molecules. Each new observation will add details to the portrait of interstellar objects, gradually transforming them from mysterious wanderers into well-studied types of cosmic bodies. Theorists aren't standing still either. Computer models of planetary system formation are becoming increasingly complex and realistic. They account for the dynamics of gas and dust in protoplanetary disks, the growth of planetesimals, planetary embryos, into planets, the migration of giant planets and their influence on small bodies. These models show that ejection of objects into interstellar space is an inevitable byproduct of planet formation. In every system with giant planets, billions of small bodies are ejected outward in the first few million years of the system's existence. This means the galaxy is literally filled with interstellar objects, fragments of planetary systems drifting between stars. Some calculations suggest that in the Milky Way, there may be more interstellar objects than stars. Of course, most of them are tiny, the size of a grain of sand or pebble, invisible to our instruments. But even large objects, the size of Comet 3I Atlas or larger, should number in the billions. We live in a galaxy saturated with these wanderers, and only now are beginning to realize it. Each discovered interstellar object is a window into another planetary system, an opportunity to learn how planets form under different conditions, what diversity exists in the universe. Beyond purely scientific interest, studying interstellar objects has practical significance too. Understanding how often such objects pass through the solar system, what their orbits are, what sizes they have, is important for assessing collision risks with Earth. Although the probability of an interstellar object striking our planet is extremely small, space is huge and targets are small. It's not zero. An interstellar object moving at high speed will have enormous kinetic energy. Even a relatively small object 100 meters in size striking Earth at a speed of 30 to 40 kilometers per second would release energy equivalent to the explosion of megatons of nuclear weapons. The consequences would be catastrophic for the region where the impact occurred. Fortunately, such events are exceptionally rare. The probability is perhaps once in millions or tens of millions of years. But knowledge of this possibility forces us to develop detection and tracking systems. Planetary defense programs, such as NASA's Planetary Defense Coordination Office and European counterparts, monitor the sky for potentially hazardous objects. For now, their attention is focused on asteroids and comets from our system. But with the growing number of discovered interstellar objects, these programs will expand their activities. Returning to Comet 3I Atlas, its story reminds us of the cyclical nature of the cosmos. Matter constantly transitions from one form to another, from one place to another. Stars are born from molecular clouds, live for millions or billions of years, then die, returning their matter back to space. This enriched matter, containing heavy elements created in stellar interiors, becomes material for new stars, new planets. Planetary systems form, eject part of their matter into interstellar space in the form of comets and asteroids. These objects drift for millions of years until they encounter another stellar system. Some are captured by gravity, becoming part of a new system. Others simply fly past and continue their journey. This is a grand exchange of matter between stars, a slow mixing of the galaxy. Over billions of years, atoms travel from star to star. Having been part of many different objects, the carbon in your body may once have been part of a distant star that exploded as a supernova long before the sun's birth. Then, this carbon became part of the molecular cloud from which our solar system formed. It entered the composition of a comet that spent billions of years in the Oort cloud. Then this comet fell onto early Earth, delivering carbon to the oceans of our young planet. There it went through countless chemical reactions, became part of living organisms, passed through ecosystems, and eventually ended up in you. This is a poetic, and at the same time, scientifically grounded story of the connection of all things in the universe. Comet 3I Atlas is just one of countless actors in this grand cosmic drama. Its journey began in another star system, possibly billions of years ago. It witnessed things we'll never see: planet formation in an alien system, possibly the birth and death of stars along its path, clouds of interstellar gas through which it drifted. Now, for a brief time, its path intersected with ours. We observed it, studied it, learned about the universe from it, and it in turn experienced the impact of our sun, not only its heat and light, but also its wrath in the form of a coronal mass ejection. This interaction changed it, albeit slightly. Now it continues its journey, carrying these changes with it back into interstellar space. In millions of years, when it encounters the next stellar system, if it does, traces of this encounter will still be present in its matter. Isotopic anomalies created by cosmic rays from our sun, microscopic particles captured from the solar wind, an altered surface where additional evaporation from the coronal mass ejection left its mark. For hypothetical astronomers of that distant civilization, if they study this comet, these traces will tell a story of a visit to a yellow dwarf somewhere in a spiral arm of the galaxy, a story of an encounter with a solar storm, a story of a fleeting touch between two worlds. In the silence of space, where sound doesn't propagate, where time flows slowly and calmly, Comet 3I Atlas continues its ancient journey. Every second it moves away from the sun by several kilometers, every hour by thousands, every day by millions. Invisible to human eyes, forgotten by most of those who heard about it in the news, it nevertheless remains real, material, existing. Its surface, covered with a dark crust of organic compounds, slowly cools as it moves away from the star. The evaporation that made it visible gradually slows, fades. The coma shrinks, tails become shorter and weaker, until they disappear completely. In a few months, the comet will return to the state in which it spent most of its existence, a cold, lifeless chunk of ice and rock drifting in darkness. But now it carries within itself the memory of the encounter. In the ice layers, in the altered surface chemistry, in microscopic particles captured from the solar wind, the story of its visit to our star is recorded. This record will exist for millions of years, possibly forever, until the comet evaporates completely or collides with something massive enough to destroy it. What does this event mean for us, for humanity, for our understanding of ourselves and the universe? On the most superficial level, it's simply a scientific observation. Interesting, unique, but not radically changing our lives. Most people will continue their affairs as if nothing happened. The sun will continue to rise each morning. Stars shine each night. Daily life will remain unchanged. But on a deeper level, such events remind us of the context of our existence. We live on a small planet orbiting an ordinary star in an outlying part of an ordinary galaxy. Around us is space of unimaginable scales, filled with trillions of stars, planets, comets, asteroids. Matter constantly moves, changes, flows from one form to another, and sometimes, very rarely, part of this grand cosmic dance touches us directly, as in the case of Comet 3I Atlas and the coronal mass ejection on October 24, 2025. These are moments when the veil of ordinariness lifts and we see the reality lying behind it. Vast, ancient, beautiful, and indifferent to our small human dramas. For those inclined toward mystical thinking, the event offers food for thought of another kind. The coincidence of an interstellar comet's appearance and a powerful solar ejection may seem too perfect to be random. Maybe there's some meaning in this, some message? Ancient cultures saw omens in comets, and although we now know their physical nature, the urge to seek meaning in celestial events remains. Some might interpret this as a symbol of the meeting of old and new, past and future. A comet from an ancient system meets the modern energy of our young sun. Isn't this a metaphor for our own path, where we constantly balance between the heritage of the past and aspirations for the future? Others might see something more mysterious in the green glow of the coma. Green is traditionally associated with life, with growth, with hope. Maybe the comet carried within itself not just ice and rock, but something more. Spores of life, organic molecules capable under suitable conditions of evolving into living organisms. The panspermia theory, though speculative, has a scientific basis, and interstellar comets could be its carriers. Of course, from a rational standpoint, there's no evidence that Comet 3I Atlas carried life or its precursors. The detected organic molecules are simple compounds widely distributed in space, but absence of evidence doesn't mean evidence of absence. We simply don't know for sure. And this unknowing leaves space for imagination, for hypotheses, for dreams about what could be. Maybe somewhere in the galaxy there exists a civilization that intentionally sends comets to young stellar systems, seeding them with life's building blocks. Maybe our own life began exactly this way, with a comet falling on early Earth 4 billion years ago. If this is true, then we're all descendants of interstellar wanderers. Our DNA preserves information that traveled through space. This is simultaneously a humbling and elevating thought. Humbling because it deprives us of uniqueness. We're not a special creation, but the result of cosmic processes that could have occurred billions of times in billions of places. Elevating because it connects us with something greater, makes us part of the galactic story of life. Conspiracy theories also found their fodder in the event. In dark corners of the internet, claims appeared that governments are hiding the true nature of Comet 3I Atlas, that it's not just a comet, but a spaceship disguised as a natural object. The coronal mass ejection wasn't an accident, but an attempt at communication, or even an attack. There was talk of secret data not being published, of strange signals allegedly received by radio telescopes during the collision. Of course, none of these claims had real basis. All data collected during observations agreed with the natural origin and nature of the comet. No anomalies that couldn't be explained by known physics. But conspiracy theories exist not because they're based on facts, but because they satisfy psychological needs, the need to feel privy to secret knowledge that others don't have, the need to see patterns and intentions where there are none, the need to believe the world is more interesting and mysterious than it appears on the surface. And in some sense, these theories are right on the last point. The world really is more interesting and mysterious, just not in the way they think. The real mystery isn't in secret conspiracies, but in the very nature of reality. Why does the universe exist? Why are the laws of physics exactly as they are? Why did conditions in our part of space turn out suitable for life's emergence? These questions remain without final answers despite centuries of scientific research. And each new discovery, each new observation, such as the collision of a coronal mass ejection with an interstellar comet, adds a tiny piece to the enormous mosaic of understanding. We're slowly assembling this mosaic, generation after generation, scientist after scientist. Perhaps we'll never assemble it completely. Perhaps it's infinite. There's always another question beyond the last answer, but the process itself is valuable. The striving to understand, the desire to know. This is what makes us human, what distinguishes us from simple automata reacting to stimuli. We look at the stars not because it gives us practical benefit. Most cosmic discoveries have no immediate application in daily life, but because we can't not look. Curiosity is built into our nature. Comet 3I Atlas, receding into darkness, carries with it part of this story of human curiosity. In a sense, it became part of our culture, our collective memory. Years later, when astronomers teach a new generation of students, they'll tell about the October 2025 event as one of the important moments in the study of interstellar objects. Perhaps books will be written, documentaries made. Artists will find inspiration in the image of a green comet meeting a solar storm. Poets will write verses about journeying through the abyss, about the meeting of worlds. Composers will create music conveying the grandeur and loneliness of space. Art and science aren't opposites but complements. Both strive to understand reality, just in different languages. Science uses the language of mathematics, observations, experiments. Art uses the language of emotions, metaphors, images. But both explore the same universe, the same human experience of existing in this universe. And events like the collision with Comet 3I Atlas inspire both approaches. In a few years, when the comet crosses Neptune's orbit and enters the Kuiper Belt region, it will become so distant and dim that even the most powerful telescopes won't be able to track it. The last observation will be noted, the last entry made in catalogs, and then the comet will disappear from human knowledge, becoming again what it was for most of its existence, an invisible wanderer in the abyss. But somewhere in the future, maybe in millions of years, it will encounter another star. Perhaps it will be a red dwarf, a dim star that burns faintly but long, trillions of years. The comet will pass through the outer regions of this star system, possibly will be noticed by hypothetical astronomers if a civilization exists there. Or maybe it will pass through a dense molecular cloud, regions of space where gas and dust gather, preparing to form new stars. The comet's particles may become part of this cloud, enter the composition of a new protoplanetary nebula. Atoms that were part of Comet 3I Atlas will find themselves in new planets, new comets, possibly even in new forms of life if conditions are suitable. The circle will close, the cycle will continue. This is the true nature of the cosmos, not static, not frozen, but dynamic, eternally changing. Matter circulates, energy flows, structures form and break down, stars are born and die, galaxies collide and merge, black holes swallow matter, then perhaps evaporate through quintillions of years through Hawking radiation. The entire universe is a grand process, unimaginably complex but subject to simple fundamental laws. And we, tiny beings on a tiny planet, have the incredible privilege of observing this process, studying it, trying to understand it. On cosmic scales, our existence is fleeting. Humanity has existed for only a few 100,000 years, civilization for a few thousand. All our recorded history fits into an instant of cosmic time. But in this instant, we've been able to develop consciousness, intelligence, the ability to ask questions and seek answers. We built telescopes, sent probes into space, deciphered the laws of physics. We moved from worshiping celestial objects to studying them, from fear of comets to understanding their nature. The event of October 24th, 2025, is a small but important step on this path. It showed that the universe continues to present us with surprises, that there's always something new to study, something unexpected to observe. It reminded us that space isn't a dead, lifeless void, but a dynamic environment where something is constantly happening. Solar storms, interstellar wanderers, magnetic fields, plasma, all these are real, physical phenomena occurring right now, above our heads, if only we find time to look up. And when we look, when we observe, when we try to understand, we become part of something greater. We become the way the universe knows itself. The atoms in our bodies, formed in the cores of ancient stars, organize themselves into a structure capable of contemplating stars, comets, the nature of existence. This is a miracle, perhaps the greatest miracle we know. And as long as we continue to look at the stars, ask questions, seek answers, this miracle continues. Comet 3I Atlas has left, but the memory of it remains, woven into the fabric of human knowledge, another thread in the infinite tapestry of understanding. And somewhere out there, in the darkness between stars, other comets continue their journey, awaiting the moment when they too will enter the light of someone's star and tell their stories to those ready to listen.